Alrighty. Tonight we're going to be skipping a live show in lieu of a pre-recorded live to tape Monday show actually. I'm recording it now on Sunday night. I do have some pre-recorded content I will be mixing with tonight's upload or premiere, however you want to phrase it. I hope everyone enjoys what I have in store. Basically, I need to get a good night's sleep this Monday in preparation for an exam. And so that's why I decided to basically alter the plan. I didn't want to completely cancel the Monday show because I really appreciate everyone coming out. So I hope I can still, provide something entertaining and informative. The basic plan is we're going to explain why. We're going to set out to explain why the moon and the sun can be out at the same time. Because I think it's a commonly held assumption that the moon is a nighttime phenomenon, when in reality the moon can be out in the daytime just as much as it is out at nighttime. Some differences might be you're not going to see a full moon out during the daytime when you can see both the moon and the sun. Typically, the moon is going to appear to be either a new moon, a crescent moon, a half-shaded moon. It's not going to be like a fully lit moon unless you have a, really optimal angle. And to understand that, I think it's going to help to be able to show you guys a 3D model of, our solar system, or at least a 3D model of the relationship between the Earth, Moon, and the Sun. Once you see what the Moon is doing in space, how the Earth is being lit, and I can explain it while showing this in a 3D model, I think it might make a bit more sense than it might make, just kind of explaining it verbally. So, basically bottom line is we're going to try to address that question. I mean, maybe not everyone in the audience has that question, but anybody who does have that question, tonight's your lucky night. Other than that, we got some footage from the GAIA catalog, and you can see like a 6-layered timeline. I'm not even done editing this, and I don't really have enough time to finish it now. But in a nutshell, this is a preview of something I have in the works regarding the GAIA catalog. Now, I didn't really get a full opportunity to really pimp this out, but we're going to try to, clean this up right now so you guys can see something really neat about this. So basically, one of the things I observed about the, galaxy when you look at it under, this type of, let's see here. So there we go. So a little starburst pattern. So essentially, the center of this pattern is where our planet Earth is located. And yet, we're only looking at one corner of the galaxy. We're literally looking at what would be considered the beta quadrant in Star Trek, or the alpha quadrant. I guess we're looking at the alpha quadrant right now, if this is Star Trek. And since we, have our, space observatories, our space telescopes, imaging everything from where we are located right now, just about everything that has been mapped is really just mapped in this one, area. And then as you get further out from this area, the stars get fewer and further between. I mean, it doesn't mean that there's not stars way out there. I mean, you could even see in this little pattern here how it is like a little dark area. That doesn't mean that there's fewer stars over here. It just means that our view of the stars that are past this dark line are being obstructed by larger and brighter objects. And so either the space telescope didn't yet measure these objects, or there are none to be had. Now, the GAIA mission measures stellar distances. It measures how far away stars are from Earth and how far away those stars are from one another. And so it allows us to make a 3D model, or view of 3D model. I certainly did not create one. What I did do is I used Space Engine's camera path editor to pre-record a camera path so that I can record the same path, but each time I play back the recording, we're able to see stars at different magnitudes. So basically, these are like the stars that like in the top setting, when I make this turn on and it gets brighter. Let me see if I can show a better example. Essentially, you're seeing different settings. In Space Engine, if you press the right buttons, you can make it reveal stars of very low magnitude. So stars that are otherwise too dim to see from far away, we're basically able to force Space Engine to make them visible. Now this has the, unfortunately this will also cause, stars to get way too bright if you get way too close to them. That is why I, basically did multiple passes with the camera path editor, and I still gotta sit down and work on this. But for now, I'm gonna just do, I'm just gonna whip something up real quick, and then we're gonna go ahead and play back a tour of the moon, followed by a tour of our local galactic neighborhood. The date is Sunday, June 9th, 2024. 00 hours, which is 8 p.m. New York. I confirmed it. I looked it up. It says that midnight GMT, which is Greenwich Mean Time, or UTC, is 8 p.m. in New York, which is approximately the time I'm walking home from work, like 8:09 according to this. And we could pause it, or we could let the time keep on crawling forward 1 second at a time in real time. And of course, we're going to just pick Brooklyn because, in fact, that's the area that we are concerned with today, is what time it was, or what the moon looked like in Brooklyn around 8 o'clock. Or we could even do 7 o'clock. So, oh man, let's go reverse a bit more. We want to see maybe the moon in the early evening before sunset. Alrighty, we are positioned right over basically Manhattan, Brooklyn, Staunton Island, New Jersey, and the Bronx. Oh, and of course the rest of Long Island. See, long ass island. That is yeah, and you got the Far Rockaway, Coney Island, etc. But from this position, at roughly ground level, I can go to the ground if we want. The moon looked like this at 6:52 p.m. Let me double check that. 2200, yeah, 2200 hours, 2200 GMT or UTC is 6 p.m. New York. Ouch, that was my ball. Okay. And the moon was out in the daytime. Interestingly, let's say we want to see the moon out earlier in the evening. Let me get my mouse pointer, or I could do it in the gamepad, but I like being able to see the date and time right over here. Five, 4, 3, 2, 1. Okay, like around 1:30 p.m. the sun is like almost at the noon position, and the moon is still flying next to it. So throughout that time now, let's say we go from like around 1 p.m. to 2 p.m., etc. The moon and sun are both going to traverse from east to west. So right now, east is the left side of your display or screen, and west is to our right, where we are looking at our screen. We're going to begin to play back. This actually goes really fast. A little faster than I expected. Oh, it's going backwards. Okay. Normal time. There we go. Okay, now it's going to go from east to west. And there's our sun and moon. Notice, can we pause this? I got an idea. I want to try something. We're going to track the moon or the sun. So we're going to do track. Okay, now we're going to go in fast forward. Now, as these both traverse the sky, the sun might get a little further away. So interestingly, earlier in our daytime, the sun was closer to the moon before it started moving away from the moon. Obviously, it's not really moving away from the moon, but now we're going to play backwards. We're literally going backwards into yesterday. And notice the moon is actually getting closer now. Now, I know this is very dizzying, but hopefully we can see through the ground and see the moon rise. Alright, that's an ocean. I think it's an ocean. Oh, there we go. So, this is yesterday, basically. So yesterday, the moon and the sun looked like they were closer. Now, where is the moon right now? It's in the ground. Because, of course, it's nighttime in New York. So we're going to rewind it. We're going to look at the moon before sunset. Hey Google, what time is 1500 GMT? Okay, this is 11 a.m. on Monday. Okay, so 11 a.m. on Monday, the sun was almost at the high noon position as it would be, and the moon was over here. So what dictates the moon being out during the day or night? Well, let's fly into space, and we're gonna have a little fun here. We're actually gonna fly in, and oops. Okay, we're gonna go back up again. So right off the bat, you can always see the sun once you're not on the planet, because, you know, the rest of your own planet is not blocking the sun. Unless you're behind the moon or your own planet, you can always see the sun, basically. From this angle, the moon still has a crescent on it. And you can see how we can rotate around it and see that it's always half lit. So as it's orbiting the Earth, it is always half lit. And of course, both the moon and the Earth are sort of doing this. So you got light hitting the moon on one side all of the time. In fact, we can see it like how like one side of the moon is always lit. And same thing on the Earth. So now we're going to go back home. Half lit. And if we go on the opposite side of New York, oops, excuse me. Okay, so there's our moon. And basically both of them are totally capable of looking like a crescent from this angle. And yet both are half lit. And really the only reason why you would see the moon out into the daytime or the nighttime we could sort of simulate that in fast forward too if we want. So we're orbiting the sun all the time. So we rotate through the days, and that's what's making us see the sun, you know, rise and set. And yeah, I know it's spinning real fast. Then we're doing our thing over here. That doesn't really illustrate. Damn it. Alright, so I ran out of time on editing. I literally don't have any more time to edit. So instead we just have this spinning simulation of the moon and the Earth spinning. It's sped up right now, like we're already looking at July 30th. It's like counting 1 day per second. And in counting 1 day per second, we can see why at various times we might see the moon out during the daytime or the nighttime. Now in this case, both the moon and the sun always have one side that's always fully lit. If it was, the Earth was spinning at a more, normal speed, we could literally see the moon is over here. This would be a situation right here that would, this would be an example of the, when you can have daytime and the moon out at the same time. Because people living on the, daytime side of the Earth, they're definitely seeing the moon, except when it's flying next to the sun. Like if the moon is passing near the sun, like this would be one of those days where people on this side of the planet could see the moon until sunset. Then they couldn't see it at all. But there are other days where if the moon is like flying closer to the sun, you're gonna have a hard time seeing it. So the moon could be on the daytime side just as often as it can be on the nighttime side of the Earth. And unfortunately, I had to re-record that so many times I ran out of time explaining it properly. So instead, this is the quick example and demonstration, and we should definitely go into greater detail on that to address that question for one of our viewers as soon as we get more time to do that. Okay, begin voice recording. Alrighty, we are flying back into our home star system. Today we're going to explore the GAIA catalog. The GAIA mission involves a probe or satellite which measures stellar distances. It measures the distances between us and other stars and various stars with relation to each other. We're starting in our solar system, but we're going to very rapidly fly out. I'm not going to dwell too much in our immediate galactic neighborhood, although one thing I like to do is I started noticing, which was kind of cool, is flying out and then giving a spin around our solar system to see, if there's anything, to see if there's like, a visual way to spot our nearest neighbors. Of course, we could simply search for them or click on them, list the labels, but it's a lot more fun to do it like this, in my opinion. And also just kind of helpful to sort of conceptualize, where our neighbors are, what's closest, what's furthest. Because you can even see how, like, as I rotate, certain stars do appear to be in front of or behind one another. And so right there we got Sirius, which is seriously a bright star. We got Alpha Centauri, and if we fly into Alpha Centauri, as we get close enough to it, and we come in behind it, we can most certainly end up spotting by accident Proxima Centauri, which is this red dot right here. And of course both of these have their fair share of exoplanets. And now that we've visited Proxima and Alpha Centauri, by the way, is a binary star system, we're going to fly way out. And we're going to make sure that we put the Milky Way in front of our star. So that's the densest part of the Milky Way. And this is technically the center of the Milky Way. And the reason that is relevant, what we're going to see right now. So of course, the Milky Way has these spiral arms, and I forget if we're in the Sagittarius arm or the Orion arm. I know it did change at one time as we got more updated and accurate information, although some people believe it's a Mandela effect because they look at a news article and it says like Orion arm, and then they see a newer news article and it says Sagittarius arm. So instead of asking the people who do this stuff like, hey, what happened, they just jump to, oh, that's residue from a different timeline, hence Mandela effect. And it's like, no, this is not Publishers Clearinghouse. I mean, that's also not a Ed McMahon and Publishers Clearinghouse is also not a Mandela effect. I mean, it is one in the sense that a lot of people share this incorrect memory, but that's all it is. That's what makes it a Mandela effect. Not that it is some extra, ordinary phenomenon. That is, in my opinion, not part of it. But I could be wrong. So anyway, getting on topic, let's do the fun part here. So we're looking at stars from the GAIA catalog, or at least we're going to be looking at stars, a lot of them from the GAIA catalog. The GAIA mission measures stellar distances, and we're gonna actually increase the magnitude of visible stars so that we can see more stars from a greater distance away. And this is valuable because when you do this, you can already see like a radiant pattern. You can see like darker and lighter areas or less dense areas of stars, and that's because some of the stars that are closer to us block our view, obstruct our view of things at greater distances, or maybe it's also because we didn't get around to cataloging those stars yet. Maybe they're doing a search pattern. But there is actually a thing where when you look at a map of galaxies, it looks as though there are no galaxies along the plane of the ecliptic or along the galactic plane. So here's our galaxy from this side, and we measure a lot of galaxies above. Like there's our Magellanic Cloud up there. I think we got the Greater and Minor Magellanic Cloud, but we don't see a lot of galaxies. We don't have a lot of galaxies on the horizontal axis, and that's basically because we got a lot of stuff blocking us. Whereas looking above or below, there isn't a lot of stuff blocking us. So if we fly out, we can see how the magnitude allows us to see the stars with a dimmer perspective, or they look less bright, I should say. And next time I do this, I'm going to do it with the 5 million star catalog. That one's going to be interesting to see how long it takes the computer to process that. But for now, I just want to see the result of processing this video. So this is something that I'm going to play around with more. But for now, I did what I could to record a camera path and then to replay it multiple times with different settings so that we could effectively have layers. So I hope that was kind of helpful for kind of conceptualizing our galactic neighborhood. And with that being said, I want to thank you for watching. If you have any questions, comments, or suggestions for things to look at in this space engine, please let me know. And for now, we shall end transmission.